All right, so let's get started. Good afternoon, all. My name is Lucy Ingram, and I am a faculty member in the Arnold School of Public Health at the University of South Carolina. I am also the co-lead of the research education component of the Carolina Center on Alzheimer's Disease and Minority Research, also known as CADMR. I would like to welcome you all to our seminar for today entitled Population-Based Data and Introduction to Sampling Weights. Today's speaker is Dr. James Hardin. Dr. Hardin is professor of biostatistics here at the Arnold School of Public Health. His research interests include correlated data, limited dependent variables, discrete choice analysis, generalized estimating equations, and complex survey data. Dr. Hardin is also the co-leader of the analysis core of the CADMR. Today, Dr. Hardin will be introducing and demonstrating the use of sampling weights and how they admit inference about a population, even when the data in the sample were not collected randomly over the population. He will also be discussing why sampling designs purposely differ from simple random designs. I ask that you please join me in welcoming Dr. Hardin.
All right. Let me get to my... All right, I think I'm sharing my screen and let me get to slideshow. Up. I somehow knew that was going to happen. There we go. All right. I appreciate it. I appreciate the introduction and I appreciate your attendance to today's meeting. I've been thinking about talking about sampling weights to our CADMR scientists for some time because all of our data sets that we use and that we provide include sampling weights. And so beyond kind of explaining to people that when you have a data set that has sampling weights, you have to take those into account. You've got to use them. Beyond that amount of advice, we really don't talk much about it at all. Now, this is an area of statistics that could entertain a workshop of a week that we could talk about various aspects of survey sampling, non-random sampling, and how to go about doing an analysis. And I'm not going to do that today. So today I'm going to do something very, very basic. That is, I'm going to motivate what sampling weights represent. What kind of information do they carry? Why is that important? And then, because it's almost as important to know how to do something right, it's also important to know, well, what happens if I don't do it right? Right? What kind of problems can I foresee? And so that's what I thought I would do today, because I thought that would be of most use, especially to our scientists, to just sort of further motivate and emphasize to them the importance of these things and how you really do need to take these into account and consider them and treat them. Now, in my background, I worked for some time, about 4.5 years for Stata Corporation. And so that's the software that I use. And so toward the end of the presentation today, I'm going to fire up Stata and I'm going to demonstrate what happens when you use these weights, what happens when you misuse them, and what happens when you ignore them, just so that you can see all of the things that I can do today. We, that is all of the people in the analysis core, can help you do in SAS or R. So it's not something that's unique to Stata. I'll just tell you that it's best done in Stata because we all love to defend our choice in software. And so that's the one I use. Now, this presentation is coming to you from me, a biostatistics professor. And so I know there is some fear, and that fear is, oh my God, you're going to talk about math, aren't you? And the answer is only a little bit. I promise I'm not going to give kind of a usual biostatistics seminar where I derive a bunch of formulas and argue about the properties of the estimators that we get out of those formulas, I really am going to emphasize some very simple things. And the first is that I'm going to keep my presentations and explanations to a minimum. So you're not going to see a whole lot of mathematics in today's discussion. In fact, all I'm really going to talk about is an average, right? And we all know an average is just a total sum divided by a number of observations. How many things did I add up, and what is that ratio? And so that's all we're going to talk about, because that's all I really need to talk about to motivate what these things stand for and what they carry. And so we're going to start off with a very, very simple example. And so I want you to imagine that we've got some data, and the data that we've collected include household income, right? So we're doing this study and we kind of want to talk about the average household income. It could be for South Carolina, it could be for the United States, it could be for whatever kind of population you want to think about. And I want you to imagine that there's two different ways that we could organize those data into a file, right? There's kind of the standard way, the universally accepted common way, and then one other way that's kind of an efficiency organization. And so let's look at that. So in this first way, and this is just an example, obviously, I've got 102 households for which I've collected the household income. Now, it just turns out that in these data, when I collected them, I had 100 different households that all reported the same household income, $31,000. And then I had 2 households that each reported a household income of $200,000. So the standard sort of universally accepted organization of those data would be like this organization 1. That is, I would make a row in my data set for each one of the 102 households. I'd have this row variable or an ID variable so that I could keep track of which household was which, right? And so I've got one variable called row, and it just goes 1 to 102. And then I've got HHINC for household income that has the value of the household income for those 102 observations. So again, I've got this ellipsis sitting here in the middle because this actually is 102 rows, and that's one way I could organize these data, right? So from an efficiency point of view, another way that I could organize these data would be like this, right? In this organization, I only have 2 rows. I have 2 rows in my data set. I have an extra column in this data set, and I've cleverly called that column num houses with HHINC. And so this organization is such that for a household income of $31,000, there are 100 such houses. And for a household income of $200,000, there are 2 such houses. Okay, so I've managed to collect and kind of illustrate all of the same information in both of these organizations, right? And so I hopefully this is really obvious, and you can see that I haven't lost anything. The only thing I've lost, if you want to talk about that in organization 2, is that I've lost the individual identifiers, right, that exist over here in the first column of organization 1. So I've lost that ID variable. But in terms of the information about household income, they both have the same amount of information. Okay, so how are we going to calculate the mean for each one of these organizations, right? This is what I was talking about when I got started, that there won't be any more math than just calculating a mean. All right, so how do we do that? So let's take a look at organization 1. And so for that organization, we could just add up all the 102 values of the HHINC variable, and then divide it by 102. We could use the mean function in whatever software package that you like to use. And that total, right, the numerator of that average is just add up all these things, add up 31,000, there's 100 of those, and then 200,000, there's 2 more of those. And so that adds up to about 3.5 million. And then we could take the average is 3.5 million divided by 102. The average household income for these 102 values is $34,000, $34,313.72.5. Really straightforward. You just use the mean function in R, you say proc means in SAS, and you say summarize in Stata. Very straightforward. All of those approaches to data analysis think about data being organized in this way. All right, what about organization number 2? If we take that same approach, we calculate a total for this variable HHINC. We add up 31,000 plus 200,000 and we get 231,000. We divide that by 2 because we had 2 different values, and we get an average household income of $115,000, $115,500, right? So clearly wrong, right? Based on what we already saw in the first approach. So a different approach to this calculation needs to be entertained. And so what is that? Where are we going to get that other information? And so it's really done this way, right? That if I really want to know what's the total of all of my households, well, I have 100 households that made $31,000, and I have 2 households that made 200,000. So I really need to multiply these things together before I add them up. And if I do that, I get the right total, right? So it's just a very simple algebraic equivalence, but I have to do it in this other way. The number of observations, that is the number of households that I have, is I just add up this column, and then I get the same average. So just because I've organized it in a different way, so long as I do the calculation a little bit more carefully, I get the right answer. If I do the calculation in the normal way, ignoring the fact that I've made a more efficient organization of my data, I can be grossly wrong, right? So ignoring the fact that I have this different organization, but using the usual approach to data analysis, I overestimated that average by an awful lot, right? I said it was $115,000. But if I do this in a more careful way, I can get the right answer, the same answer as we had for our usual organization of data. All right, so here's my one formula that I am going to show you. It's just the formula for an average. So that usual formula for the average just is a ratio. It's a total divided by a number of things. And we're going to rewrite that this way. Okay, so the total is a value times the number of those values that I have. And the total number of values is the total number of these of this variable. I've used the letter R here because I'm thinking in my head the word replicate, right? So I have $31,000. How many replicates of those do I have? 100, right? So this R1 would be 100. And then I have 200,000 and there's 2 of those, right? So this more general formula works for either one of these data organizations. So let's look at that real quick. So over here with organization 1, this replicate is really just implied. It's not in the data set. We don't think about it. It's just the number 1, and 1 times anything is just that thing. And so we always just leave it out of the usual formula. But in organization 2, the number of replicates is this other variable that was sitting in my data set the whole time when it was provided to me, right? I just needed to know that it existed and that the data were organized in this other way. And so this I equals 1 to n, right? This n that usually we all think of as the number of observations. We have that ingrained in our brain, me too. Doesn't mean that anymore. It's really just the number of rows in the data. The number of observations is the sum of R sub I. Well, the sum of 1, if you put a 1 down all of these things, is really just the number of rows. So we haven't lost anything, right? By doing this, we just need to know what's R sub I and why do I have that, right? So when you write it down this way, that R sub I can be interpreted a couple of ways. I've been presenting it as replicates, right? How many households have this particular value, right? And so another way to say that would be it's the number of households that are represented by this value in my sample, the number of such values that this value represents. I'm doing it right now, showing you this with these replicates in terms of the sample. But I could very well think of this in terms of the population, right? How many households in the population make 31,000? And I could have an R sub I for that scale. That's really what a survey weight does, right? A survey weight is just representing how many of these values really exist in the population, right? Because taking that into account gives me the right answer, right? So when I took these replicates into account, I got the right average, right? When we were doing our sample means. Same thing happens with survey weights. When you take those into account and utilize them and recognize that the information that they're carrying is a weighting, right? Is a representation. How many of these things, how common is this particular value in my population? So once I do that, I more faithfully represent the information that is out there in my population. Okay, so we're going to switch gears just a little bit and talk about why does that come about? Why do we need those survey weights, right? So what we've learned is that when we want to estimate an average, we can think of that as a value along with how many such values there are in the sample. Just as we saw in the initial few slides, if you don't properly incorporate those weights into your calculations, you won't get what you intended. Your data treated with by ignoring all of those sampling weights will lead you to calculate something that doesn't represent the population that you're really after. And so those replicates are directly comparable to the function of survey weights. So survey weights play that exact same role. The only difference is that they're related to the number of similar households in the entire population instead of just in the sample. Why do they do that? Because we want to know what's the correct average for the population, right? So these survey weights are provided to us. They increase or decrease the number of times each value is incorporated into a calculation. So I'm changing the way I say these sentences only a little bit. What I'm trying to do is make sure that at the end of this, you don't think, oh, that works for the average and that's it. Actually, it's the exact same thing in, let's say, estimating a regression model. Those weights are increasing or decreasing the number of times each row of the efficiently organized data contribute to our model, right? And so they do so by by basically inverting the probability. And so we're going to talk about that and see that a little bit. Okay, so we're going to go over one more generalization, and that's the idea of a subpopulation mean. So imagine that there's 4 different subpopulations, right? So I want you to imagine there's a population of interest. Maybe it's 4 states, right? Tennessee, Kentucky, North and South Carolina, right? We're going to do our study for those 4 states. That's our population of interest. At the end of this, after we've collected our data and we've estimated our models, when we talk about what we learn, we're going to be talking about the average for people in those 4 states. Now, when we do that, we might be interested in talking about each of the 4 states, right? So we can think about the population of the 4 states being comprised of each of the 4 states, right? And so that I chose that example in particular because I want you to think of subpopulations that are mutually exclusive. I don't want you to think of populations that overlap, right? Like populations of race and populations of sex where they might overlap. So we'll just imagine, to keep everything simple, that subpopulation 1 has a mean, right? And that mean is mu sub 1, and it has n sub 1 observations. So we'll just use these subscripts for each of these 4 subpopulations. So this is the way, hopefully you're just thinking about this. The overall rectangle is the whole population. Each one of the squares within the overall rectangle represents each of the subpopulations, right? This is very typical in the analyses that you want to do. You might be thinking of race, right? If you're looking at incidence of Alzheimer's, you might want to separate out and estimate the effect of age for each of several different races. And so you might be thinking about it this way. I do want to point out that most of the time, this is a more accurate picture, right? These 4 states don't have nearly the same populations. One's going to be a lot bigger than the other. When we think about the number of each race that might be included in a given data set, it might look like this, where we have a whole lot more of one race than another. And so, but we think about it this way, and this is the reality. So when I stare at this picture and think about the 4 subpopulations that exist out in my overall population, I start to worry a little bit, because organization 1 of the data, the standard universally accepted organization, is the result of simple random sampling. Simple random sampling says, I'm going to think of the entire population of all 4 states as one big group. Everybody has an equal probability of being selected into my study. That's the assumption. And now I'm going to go and take a sample. Well, unless my sample's really, really big, I run the risk that maybe one of the states won't be represented. One of the races won't be represented. That might happen in what I'm doing, right? And so I need to change the way I think about going out and getting my sample, right? I've informed my funding agency of my intentions. My intentions include an interest in comparing whether 2 races are the same, right? And so therefore, I need to make sure that I have representatives of each of those races in my final sample. So instead of taking a simple random sample, I very purposefully go out and ensure that I have representation from each of the 2 races, right? So I might do what's called a stratified random sample. That is, I think of my overall population as being made up of race 1 and race 2. And I go and get a certain number of observations from race 1 subpopulation and a certain number of observations from race 2 subpopulation, right? So what I have now would be incorrectly analyzed if I thought of it as organization one, especially if the two races were vastly different in sizes within my population. Why? Because when I do that, I'm more likely thinking about this picture. I'm more likely thinking that they're equally represented. At least my analysis will result in that assumption, right? And if that's a bad assumption, I don't want to do it that way. So how do I make sure that I don't make that mistake? And the answer is that the people who have drawn the samples for you, who went out and did that, are going to include extra variables in the data set that include sampling weights. And so those sampling weights are going to adjust for the fact that we didn't do a simple random sample. So I want to ensure that everybody understands the total number of observations we can just think of as inverting that formula for the mean, right? The mean is equal to the total divided by n sum 1. So if I wanted to just think about the total, well, it's the mean times the sample. So we keep that in mind so that we know that the total for the entire population is just being able to add all of those things up. The total number of households for the entire population is just the total number in subpopulation 1 plus subpopulation 2 and so forth. Knowing those things is all that is needed in order to construct these sampling weights, because what happens is they think about, for your particular sampling design, what's the probability of a given household being included in the sample, right? Given that I'm very purposefully going to get N1 from subpopulation 1, N2 from subpopulation 2, and so forth, right? Since N1 through N4 are different, those probabilities are going to be different. The sampling weights is just the inverse of that sampling probability. And so it becomes the number of households that are represented by this one observation. It's the same thing as what we did in the first couple of slides. Okay. The average for the whole population just looks like this, right? It's the total divided by the number of observations. So just using those kinds of things is how these population weights are created. So I want you to imagine we've got a sample from this population, and if the sample were simple random sample, we would have a bunch of households that were chosen across the entire population. Everybody would have an equal chance. That is, how many people am I going to sample divided by how many people are there, right? So if there's 1 million people and I'm going to collect 100, well, then each person has a 100 out of 1 million chance of being included in this sample. But if that's not what we did, right? And so the sampling weight just turns into the reciprocal of this probability. It just turns into n over n. That is, each person that gets included represents 1 million divided by 100, right? They represent those 100,000, those 10,000 people. So there's 100 observations, each one representing 10,000 people. So the total representation is of the 1 million people. So that's all that the sampling weight is. When the sampling weight's constant like that, we typically ignore it because it all cancels out. It's when that probability is not constant that we run into trouble, right? So in this first approach, if we just do a simple random sample, we might be able to estimate our subpopulation means, but we might not have any observations from some subpopulations in our simple random sample. So that's the weakness. The strength is that it's very straightforward. all the weights are the same, we can ignore them. We can use all the usual straightforward approaches, and we will be correct. The weakness is we might not be able to estimate everything we want, and that's going to be a serious problem if we've told our funder that one of the things we're going to assess is whether two subpopulation means are the same. We can't estimate one of them. We're in terrible trouble. Okay. So to overcome this weakness, we can draw different kinds of random samples. Instead of just randomly selecting some households, we can purposefully choose a sample to get a specific number from each subpopulation. So again, this is just another picture of what I've been describing. Hopefully, this is becoming a little bit more clear. I'm going to extend my example of non-random sample to slightly more complicated. We can think, if we think back to our 4-state example that I presented to you, those are our strata. So we could say, I'm going to get 100 observations from each state. Within each state, I can then further talk about a non-random sample, right? So instead of just getting 100 random people from South Carolina and 100 from North Carolina and so forth, within each state, I could purposefully get 50 men and 50 women. I could purposefully get any other kind of thing that I want that's not quite random. All right, so now that you've sort of seen where these things come from, and I hope you have a appreciation and an understanding that sampling weight is just basically can be interpreted as how many things, whatever it is, right? In our example, it's been households. How many households does this particular observation represent? 100, 10,000, 1? Is it a very rare kind of thing within my population, or a very common thing in my population? And by then weighting, applying replicates in the appropriate way, we are able to estimate the population statistics. All right, so I'm going to switch over to Stata and show you what happens here. Sorry, I constantly have to move your pictures around. Okay, so sorry for the font size here. By the way, everything that's in this little do file, which is a script file to run this example, it's written in such a way that anybody can run it. All you need is a copy of Stata. It's included in the last 2 slides that I have sent over to Quentin. And so Quentin, if you're going to share them with everyone, all of this stuff will be there. You don't have to race around trying to take notes or anything like that here. Okay, so what I wanted to do was to start by just using a typical data set that's available. So Stata has made available the second National Health and Nutrition Examination Survey. This is the NHANES 2 data set as our examples. This is a very typical kind of data set being used throughout public health. Maybe not so much with CCADMR because it doesn't have everything we would need. But let's just take a quick look at it, right? So this data set I just loaded, downloaded from the internet and loaded, has a whole bunch of different variables in here. It's got a unique case identifier. It does have strata in it, and so it's got 32 strata. It does have a primary sampling unit. It talks about region and SMSA for location. It's got household size and a bunch of other things. Down toward the middle, let's see, is this. It has a variable in here called final weight, right? And the label on that variable says, this is your sampling weight, except for lead, right? They have another sampling weight for lead. So if you want to analyze lead, the amount of lead, I think this is blood results. And so the amount of lead that can be found, you need to use this sampling weight. If you want to use any other outcome, you use final weight. Okay, so that's what that says so far. And we've seen it, so it's in there. So if I take an interest in, let's say, zinc, right? So the amount of zinc, I can summarize that variable and I can see, hey, there's 9,189 observations in this data set, and the average zinc level is 86.5, right? It goes from a minimum of 43 to a maximum of 240. So I can find all that out by doing that. But when I just did that, what did I do? I calculated all of those statistics, assuming that every single row in this data set was the same. I'm treating it like organization one, but we know we shouldn't do that. So we're going to go back up here and we're going to communicate to the Stata program how the sample was done and where our sampling weights are. Okay, so with Stata, you do that with what's called the survey set command. So survey set communicates to Stata, hey, the data set that I have loaded into memory right now is actually a complex survey weighted data set. So everything I ask you to do, I want you to keep that in mind. And so I have to communicate to Stata, where is that information stored? So I tell it, by the way, there's an ID variable called PSUID that identifies the primary sampling units. And I have another variable, final weight, that I want you to use as my probability weights. That's what Stata calls sampling weights. And furthermore, this was a stratified sample. And so to find out which stratum each observation belongs to, you need to look in this variable. So I had to communicate a lot to Stata. So I do that, and it responds to me saying, hey, I understand you've got sampling weights. I understand that you want me to calculate standard errors using the usual sampling approach, complex survey weighted approach. We don't have any single units. This is a numerical difficulty. Imagine that if you were thinking about clusters or surveys, if somehow your Strata variable or your only included one single sample from a given stratum, that would preclude you from calculating a standard error. You need at least two things in order to calculate a variance. You only need one thing to calculate a mean, but you need at least two. So Stata has this little line in the output saying, hey, we don't have any of those, so that's good. And here's the name of the variable that I'm going to use for sampling unit one, and here's the name of the variable that I'm going to use for Strata. That's great, and you don't have to spend a lot of time worrying about that, right? All you have to worry about is, did I communicate everything I needed to? And once you do that, Stata is going to take care of it for you. Same with SAS, same with R. Once you communicate all of the variables and their role in the complex survey that was undertaken, then it does the right thing. Okay, so how does it do the right thing? So we'll go back to our code and say, well, let's type survey and give me the mean of zinc. And then just for fun, we'll do it the wrong way and see, well, what happens when you do that, right? So I run that. And so when I say, hey, using all the information I gave you about my complex survey weighted data set, please calculate for me the average for zinc right? So what's it going to do? It's going to use that other formula. It's going to use that RIXI divided by the sum of RI. It's going to do that instead. And while it does that, because it knows that these complex survey weights are the inverse of the probability of being included from the population, because it knows that, if it just adds up all of the sampling weights, it knows the population size. So it tells me, hey, by the way, this sample is taken from a population with 104,176,071 persons in it. We have 9,189 in our sample. We've got 31 strata and 62 different primary sampling units, right? And then here's the answer, 87.2. And here's our standard error of this, right? Why do I need a standard error? I need that from my 95% confidence interval, okay? So we're just doing very simple things right now, just calculating means. What happens when we ignore the fact that we did not take a simple random sample and we use approach 1, organization 1? Well, we get a mean that's 86.5. It's only slightly different, right? In my contrived example, I made them vastly different just to make a point. Down here, slightly different. Now it gives us a standard deviation when we do this summary, and that's only so we could look at the standard error, but here it is. So when I do the mean of zinc, I get 86.5. It's the same thing. It's just the simple mean, right? This is, I ran it both ways to demonstrate to you that this mean is actually just pretending 1 over n sum of x. It's the same as the mean command. All right. And it's got a standard error of 0.15. Now the standard error up here is 0.49, much larger, right? So even though we didn't mess up too terribly in our estimate of the mean zinc levels of our people, the standard error was way off, right? It's nearly 0.5 when we take everything into account, but down here we think it's 0.15, right? What happens when we underestimate our standard error? Our statistics get bigger, our p-values get smaller. We start making type 1 errors. We start saying things are significant when they're not, right? So that's the result of doing this in the wrong way. All right, let's continue down and see what happens if we don't communicate everything that we need to communicate, right? So just for fun, I'm going to tell Stata, hey, my data set has a unique identifier and it has p weights, sampling weights, but I'm not going to tell it about the strata, right? What happens then? Well, what happens is we still get 87.18, right? Just as we did before, we still get the same point estimate, right? But if I don't tell Stata or any software package about everything that was different about how I collected my data, I'm going to get a different standard error, right? So my standard error increased in this particular case, right? When that increases, the statistic decreases and the p-value goes up. And so by not communicating everything that I could have, I might not find something that's significant. So I might commit a type 2 error, right? So you can see both of these things can result. Let's continue on and just do a quick regression. So I'm going to survey set the data again correctly, and then I'm going to run a regression and I'm going to compare it to running regression, ignoring the fact that I need to use my sampling weights, right? So, okay, this is the result of the regression model. Okay, I can fit everything on there at once. And so 31 strata, 62 PSUs, all of this summary information is the same, right, about the total population size. And then we get our regression model. So what is my regression model in this particular case? It's zinc level. I want to know about the zinc level as a function of age and age squared. And then weight, female as opposed to male, black as opposed to white, and other race as opposed to white. So white is the referent level down here, and then rural as opposed to urban. And so you can see that we get these coefficients and we get these standard errors. Well, that's in this particular demonstration, that's only meaningful insofar as how does that differ from making the mistake of ignoring that information. So here's the results for ignoring that information. So I want you to focus on the coefficient on age is minus 0.09 with p-value of 0.16. Correctly, it was minus 0.17. So we're really sort of underestimating the coefficient when we do it wrong. We've also got a really different p-value, nearly significant when treated correctly, not close to being significant when done incorrectly, right? Overall, what's happened in here, and I am including this again so you don't have to scribble a whole bunch of notes. Overall, what's going on, and I've left it in here as a comment so that you can see it. The point estimates are 3%, very, very close, to 100% different, nearly doubled, right, in size different. And the standard errors for the correct model are 30 to 110% larger for the correct model. So in this case, what's going on again, when you ignore the fact that you did not do a simple random sampling and you don't use your sampling weights, you get p-values that are significant more often than they should be. Right? Not in this particular case on age, but that's what happens because you're underestimating these standard errors. So if we look at these 0.06, 0.006, 0.006, 0.01, and so forth, and then scroll up to what happened up here is 0.08 instead of 0.06, 0.0086 instead of 0.0006, and so forth. So these standard errors for the actual population that we want to discuss are actually bigger, right? And they're bigger because of the fact that we've included a bunch of information from improbable representations in our sample, right? Because we purposefully said, I want to get representations from each of these subpopulations. Some of those subpopulations were very, very small. So the weights on them go down. And so we get a different answer. So what have we learned? Hopefully what we've learned at the end of this hour, a very quick hour, it feels like, is that sampling weights are very, very simple. They're just the inverse of the probability of being selected. And in that sense, they're just basically interpreted as the number of like items in the population, right? So if I summarize final weight, it has a minimum of 2,000 and a maximum of 79,634, right? So if you thought about just those two rows in the data, one of them, there's 2,000 like persons, and the other one, there's nearly 80,000 like persons. So a difference in scale of 40, right? And so if you ignore that scale, you ignore an awful lot of information. You assume something, a completely different kind of a population. And so that's what happens. So when you look at these data set and you get them, take the time to read through the description of what the complex survey weight is. Sometimes you'll be faced with having to use different weight variables depending upon which outcome you're looking at. And that's fine. You just have to change what you communicate to your software package so that it will do the right thing. Some will be more complicated. Some will include strata. Some will include clusters. What does that mean? Well, sometimes in a sample, we'll say, I'm going to choose random households. And then I'm going to call that random household, and a random person within that family is going to be selected of all the people over 18 within that household, right? So sort of a two-step process, right? There's the probability your house is selected, and then the probability you're selected once your house has been selected. So there's multiple sort of stages within the design of how we finally got to the person to elicit information, right? And so each of those things will be represented, the information associated with each step will be associated with one or more variables in the data set, and the documentation on your data set will communicate that to you. Your first step is to contact us, talk to us and in the analysis core, and we will very happily explain to you what role each of those variables plays so that you can communicate that effectively to your software and get the right answers. And so I'll stop there. I meant to leave a little bit more time for questions, but we'll see what happens. I'll stop my share just so we can see each other better.
Thanks so much, Dr. Hardin. Very fantastic presentation. And you led it by saying it was a semester's long worth of information. So impressed that you did that in 54 minutes or less. Dr. Deco has raised a couple of questions and comments in the chat about power. Yeah, both were related to power. Could you calculate power using different sample sizes? Since this is from a database, in your example, it's approximately 9,000 samples sufficient to infer about a population of 100 million.
Yeah, it's a great question, and so and a great question that should be asked of us in an analysis core again before you start to go do your analysis, right? Especially if you're using existing data sets with sampling weights in them, we could definitely just tell you how much power you will have to be able to detect certain differences. How do we do that? Just as I was showing, right? By using the mean functions, we can get the standard errors. Once we have the standard errors, we know the kinds of differences we might be able to declare as being statistically different. And so we definitely can help with that. Yes, 9,000 sample, a sample size of 9,000 is absolutely sufficient for certain kinds of comparisons, depending upon what kind of difference you might want to see. But 9,000 is a nice size.
And I just want to personally say thanks, James, because I really appreciate the teaching approach of kind of sharing what happens when you fail to do something optimal, right? So what happens when you fail to introduce the sampling weights? So very good. So we do have about 4 more minutes if there are any other questions or comments for Dr. Hardin. Right, we have one from Dr. Lee. How do we apply weights in subgroup regression analyses? For example, male, female.
Yeah, so I'm gonna first admit it's a terrifically long answer to tell you how you make those weights. So that's the semester long part. How do you account for those weights using a data set? And the answer is they'll be in there. There'll be multiple weights. And so come talk to us. The answer sometimes is you have to multiply those weights to get a final weight if you're using both of them, right? Sometimes it can get even more complicated. Imagine that something is longitudinal, right? And so your weight changes every year, right? Now, once you get into the study, you're in it, right? And we're going to follow up every year. But the total population size is going to change every year, and the weight is going to slightly change each year. And depending upon the type of analysis you want to do, right? If you want to use all of the observations, which year's weight should you use, right? Or if you want to just use one of them, right? And maybe it's not the same year for everyone. Which year's weight do you use? And the answer to that is complicated. And I love thinking about those kinds of things. So bring those problems and questions and your data set. We'll happily work through that.
Great. And another question actually related to what to bring you as a member of the analysis core. So Dr. Friedman asks, if you are new to a data set and wondering whether the survey has considered these topics, what is the first question to ask the analysis core team?
What is the first question to ask the core team? So that's a good question. So a description of what it is that you want to accomplish, right? Which data set you're using, and then we will go through the data set variables to see what kind of information about the survey is in there. And then we can answer the question. I noticed Benke also asked about sampling weights and subgroup sizes and things like that. And so very sort of quickly, I showed you that Stata made a comment about there being singletons in certain strata or clusters. And that problem is insurmountable for the most part, right? Most software packages are going to drop those strata. And then you need to what you need to understand when they do that is that now your population is different. Your population doesn't include that stratum, right? So you always have to, now it's on you when you talk about your results. I'm talking about all the people in these 4 states, except for the ones in this county of North Carolina, let's say, if that was the problem.
Very good. And then there are 2 more comments in the chat. I'll let you decide which one might take a minute or less to respond to. We've got Jean Kai's comment and another comment from Dr. Lee. Now, Lee.
Yeah, so if I am to look at association between lead and cognition, should I use sampling weights for lead or the overall weights? The answer to whether you should use sampling weights is absolutely. If there's sampling weights in the data set, you should definitely use those, right? Because each, you mentioned specifically lead and cognition, but they're both on the same row. And the question is, how many people does that particular row, both of those variables, representing? And so just because you're thinking in your head about multiple variables, the sampling weights are thinking about the row. And so, yes, you've got to use that.
Fantastic. You want to take a stab at the growth curve modeling question?
So I think I touched on that, and that was you want to do growth curve modeling, and depending upon how the sample was done over multiple years, you may be faced with a data set that has 1 weight. Great. It's the only one you have, you use that. You might have multiple weights. That is, you might have weights that differ for each year. So you've got an organization of your data where, let's say there's an ID for James Hardin, and there's 4 rows for my ID, right? And in those 4 rows, I have 4 different weights. And so the answer is sometimes we have to multiply them together. Sometimes we just use one of them, depending. And so it depends on exactly what model you're using. So it's not a simple answer, unfortunately.
Right. Well, use those emoticons, emojis at the bottom to thank Dr. Hardin for, I echo Benke's sentiment, making this, I'll say, simpler to understand as opposed to being simple. Thank you all. There's one more question, sorry, from Jason.
Yes. Yeah, in real life survey data, there are always missing data and non-responses from different subgroups. Would that potentially be a weighting variable that needs to be considered? Yes, and this is my one time where I'm not exactly sure that all software will do the same thing. They're going to try to do the same thing. In Stata in particular, This is why it's so important in Stata. Once you survey set and you've communicated this information to Stata, so long as you always say survey and something and use the subpopulation option, when something is missing, it's going to do the right thing, right? If you say survey fit this model if this other variable is not 0, now you're subsetting the data separately from the survey support doing it, and it won't do the right thing. So again, another really good conversation that can happen with the analysis core for those kinds of things. I don't want to end on that without emphasizing that's a very strange thing, right? So sometimes wanting to run a model and say, well, I only want to do it for the males. That's fine. But when you do it, there's always multiple ways to do anything in any kind of software. In Stata, you can say if, right? I want to fit this regression if female. But the right way to do it when you have survey data is that model, comma, subpopulation female. Then the survey collection of commands is handling your subsetting. And that's where this really happens, Jason, is that comes up. But it's a great question. And it's really, really complicated. That might be in the second semester.
Very good.
Yeah.
Well, we're all ready to register for that class, right? We echo Jason's sentiment. So this was quite the teaser. So stay tuned, everyone who's here, and tell a friend that we've got some amazing presenters and seminars that are hosted through our CCADMR network. So in terms of our final wrap-up announcements, first is a way to ensure that we continue to deliver quality, timely, and relevant content during these seminars. We ask you to complete a brief survey about your experience today. To access the survey, you may scan the QR code that you see there or complete the survey once you're emailed a link at the conclusion of the seminar.